Welcome, astronomy students, to week 14. I'm going to go through the stuff that is needed for this week. Next week, we don't have class. We don't have any assignments because of the fact that it's a holiday. It's Thanksgiving week. This week is important. I really did not, usually we start the week on Monday, but this week I did not really want to start it on Monday because of the fact that we have an exam on Tuesday. We still have the review, which is due on Monday. That's why I wanted you guys to have as much time as needed for the review. I already sent several messages for the students who did not do the review. So hopefully by this time now you have completed the review. And of course, this recording is not going to be available until Tuesday. Therefore, you're not going to be able to see the review by now. And you'll actually have the exam available. The midterm is available. So let me share the screen. Let me prepare it first. And let me share with you the screen for the objectives for this week. Obviously, the midterm, it's due on Wednesday, but it's available on Tuesday. By the time this recording is posted, the midterm is available. I urge you guys that you would take it as soon as possible. We also have something very important this week, which is this Saturday, is the final report for the lunar observation is due this Saturday. So immediately after you're done with the exam, make sure you complete that. That's a big chunk of your grade. Also, we have a homework that was extended to this Saturday because some issues apparently some of you ran into. And I made a posting and I posted it last week to help you guys with the homework. So hopefully you would have a chance to go through that. And of course, the discussion from the previous week is due on November 19th, which is this Friday. There is something in here that is not mentioned, but you will see it in the week, and I'm going to update this objectives by the time you guys are going to see this. Is going to be here, and that is the discussion for week 14. Week 14 discussion is going to be due after Thanksgiving break. It's going to be actually due on Friday, December 3rd. So I'm going, by the time you're going to be watching this, if you come in here, you're going to see discussion week 14, and it's going to be due Friday, December 3rd. The objectives for this week are in here. So I'm going to go briefly through them. And basically what they are, they're going to divide stars into two classes, basically. Low mass stars, and we see their evolution and how they end up with. Of course, they're going to end up in the white dwarfs that cool down over time to become basically dark dwarfs. And more massive stars, they could end up in one of two scenarios, either as a neutron star, or if they are too massive, as a matter of fact, they could end up in a black hole. So we're going to talk about that, and we'll see their evolution more or less on the HR diagram. So let me get into the content for this week. I'm sorry, that's actually the exam. That's fine. I'm not going to take it. So I'm not going to. Okay. Anyway, so the exam, I mean, that's a good thing that what happened now. Immediately after you see the objectives, you will see the midterm. So before you get into the content, for this week, you will see the stuff that is due. Units 63, 65, and 67 are not part of this midterm. Okay, not part of midterm 2. It's only up to unit 62. So then you have the instructions and the review, you know exactly what's covered. So if you go in, that's the units that are covered in there. Again, units 22, 23, 24, 25, 39, 41, 47, 48, 49, 51, 52, 53, 59, and 61 or 60, I don't remember the exact number, one of them, and 62. Anyway, the point, 60 and 62. Those are the ones that are covered in the midterm. So you take that, and then you come in here for units 63, 65, and 67. And it's basically two ideas, how stars die and how heavier elements other than basically hydrogen and helium are formed. They are formed, of course, inside the stars. Up to iron, they are formed in the core of stars. Beyond iron, they're formed during the supernova event for the more massive stars. That's basically in a nutshell what the story is. Okay, so this is the whole idea with it. A low mass star like the sun does not have enough mass, enough hydrogen, if you wish, in it, or enough, hydrogen to continue on burning. So this is basically in a nutshell the process. For a low mass star like the sun, inside the core, or inside its core, the temperature is high enough, around 15 million Kelvin, for its to fuse that hydrogen and form helium in the process. Okay. The radius of the sun or the star like this one starts to increase, of course, because you're producing more elements, and that the reaction there is increasing, is inside there more or less at constant rate. The reason why it's constant rate is because you have the pressure from the nuclear reaction trying to expand, basically. It's an explosion, really. But then you have the force of gravity bringing things down. When these two are balanced, exactly equal, that is basically what the star is during its main life cycle. But then when it runs out of hydrogen in the core, or the hydrogen drops below a certain critical value, at that point, of course, there is no pressure. So the star starts to collapse on itself, which increases the temperature inside because of the kinetic energy being converted, the gravitational energy being converted into kinetic energy, hence increasing the temperature. The temperature will rise high enough to the point around 100 million Kelvin, where at that point, helium starts to fuse, forming heavier and heavier elements. So in a sense, the balance is restored because there is outward pressure now from the nuclear reactions involving helium and the gravity that is trying to shrink the star. The star would expand at that point. Okay? And until it runs out of helium, at that point, basically, it's going to collapse and there is no stopping it. It's going to become a white dwarf. Of course, it's going to shed some of the materials that are in the outer layers. Those are going to be recycled during the other stellar formations. And then the white dwarf is left over, basically, from this one here, from the whole process. This is explained in here, and this is confirmed by observations. For a more massive star, though, the life cycle is a lot shorter because it has more fuel. It's going to burn faster. So it's going to go through the main stage cycle, main sequence cycle, I should say. And then after that, usually it's a few million years, depending on how more massive it is. If it's very massive, it's going to be shorter, actually. And then after that, it's going to migrate outside of the main sequence, basically, and starts to grow in size, because at that point, the star, again, for the similar process, starts fusing helium. But then, as it shrinks, it runs out of helium, it starts to fuse the heavier elements because there is more material trying to shrink. Hence, the temperature can go more than 100, 200 million degrees. As a matter of fact, it can reach the billions of degrees in the core, enabling heavier and heavier elements to fuse. Carbon fusing further, now the oxygen is involved, until you reach iron. All of these nuclear reactions that involve fusing lighter and lighter elements, albeit slightly heavier as we go along, they produce energy, hence balancing the inward, basically, pressure coming from the collapse, from gravitational collapse, producing enough outward pressure from the nuclear reactions to balance the inward collapse due to the forces of the gravity. But as you reach iron, the nuclear reaction really cannot produce, it's what is known in chemistry, actually, as an endothermic reaction, meaning it requires more energy to produce iron than to try to fuse iron to make heavier elements. So at that point, yes, you can make iron, it's still okay, as long as you can make iron, but you cannot pass beyond iron. So the star in this case, there is no outward pressure, there is no more energy produced after that point, so it's going to continue to collapse. As it's collapsing, of course, the temperature increases, and now you have this inward pressure. There is actually another pressure that is going to get involved. As a matter of fact, it's involved also on the white dwarf, and that is the so-called electron degeneracy. Let me explain where this is coming from. It's coming really from quantum mechanics. Electrons, protons, and neutrons are all what is known as fermions. They cannot exist in the same quantum state. Basically, two electrons cannot exist in the same quantum state. So you bring two electrons and bring them closer from one another, they cannot be in the same spot with the same energy level. So at that point, there is a separation. They resist that. And this is coming from a principle in quantum mechanics called the Pauli exclusion principle. So at that point, there is not enough forces to overcome them, at least for the white dwarf. However, for the case of massive stars, it's still going to continue until it overcomes even that pressure. So the reason why a white dwarf will not collapse any further is because of the exclusion principle, because of the electron degeneracy. At that point, that's it. That's the point, because there is not enough pressure to force those together to overcome the quantum forces, if you wish. But for the more massive stars, there is enough force to do that. As a matter of fact, for the less massive, but still massive stars, what happened in this case, the electron is forced to fuse with the proton and make a neutron out of it. So all of the electrons basically combine with the neutrons, in addition to the existing neutrons, is the star, the leftover in that case, is made up out of neutrons. This is what a neutron star is. There is an even more drastic scenario, and that is the collapse can even overcome that to the point where the force of gravity will overcome that, where actually the everything will collapse into a single point in space. And that singularity, if you wish, is what is a black hole. Okay, we're going to get into the details of neutron stars and black holes, and also dark matter in the week after Thanksgiving. Those are the units covering these three things. So this is just basically the evolution of a star. Again, this table is an interesting table. It tells you basically, for the case of a star like the sun, you may reach 200 million Kelvin. You may reach even 600 million Kelvin, because the process, you have probably enough collapse to raise those temperatures. But for a more massive stars, you can fuse even heavier and heavier elements, up to iron, as I was talking about. For that, you need about 2.5 billion Kelvin. This will take about a day. Usually the star, this is why you hear it so often, when it starts producing iron, it had signed its own death. At that point, there is no more. It's going to go into a supernova, which is very bright, and the remnants of the supernova, either a neutron star or a black hole, depending on the size of the star. So this is, in a nutshell, the concepts that are covered in here. Please don't forget that we have the survey also at the end of the week. I know I mentioned the midterm, which is due the 17th, which is Wednesday. We also have a survey for how the class is going, so that we can hopefully make the necessary changes at least before it's too late, or also to benefit your peers down the road in the next semester and so. In addition to the midterm, in addition to the other assignments, as I was talking about, the homework, and in addition to the discussion sessions, and in addition also to the project. In terms of other assignments in the future, past this assignments that are due this week, I can tell you what they are. On December 3rd, you have the discussion from this week, and you will have a discussion also from the week after Thanksgiving, and you will have another discussion also from the week after that. So you'll have basically the discussion from this week plus 2 more discussions that are due, in addition to a quiz that is still out there from the week after Thanksgiving, and another homework that is due from the week after that. So those are the 2 assignments, and then you have your final midterm, which is the early on in December, and that's going to be mainly all of the assignments for this class. So I did not really mean for this recording to be too long, so this is a good point to stop. Thank you.